Hello, hello, and welcome to our last topic in topic 3. I guess our last little topic here. We are going to be discussing related rates. So we've already checked off implicit. We've already done inverses. We are finishing with related rates. We're actually going to spend 3 days on related rates. And then we will conclude with a review and a nice little project. No test for this topic, so nothing too scary. So yeah, we might as well jump right into it. Your opener has 2 questions, A and B. Your goal is to find or prove that dy dx is equal to this, and then a little bit weird, dy dt equals that one. So you might even be able to figure out what you need to do to each side. And once you have accomplished that, please go ahead and unpause the video and we'll see how you did. All right. Well, the giveaway here, if we're looking for dy dx, that's probably a good indicator that we need to take the derivative of both sides with respect to x. So I'm going to set up my ddx over here. Let's zoom in like so. And then we're also going to have to, of course, find ddx of 6. That's nothing too weird. We have x and we have times a y squared, separating that with multiplication to show that we're going to have to use the product rule. And oh wait, we get to use another product rule over here. So we have x cubed, and then we'll switch colors times y, and that should be good. Of course, I left a giant gap there, so don't judge me too much. Here, we'll do that. Ta-da! As we move on down, we still have clearly an equals 0 over here, and then we have a bunch of product rule stuff. So we're going to have x, and there's going to be a little plus in between, and that's this guy with a plus and then a little bit more space. And then we have minus, and we want to make sure we subtract the entirety of the second product rule over there. Otherwise, you're going to forget to distribute that negative, and you'll miss a sign somewhere at the end. So we have a derivative. We're keeping something the same. We have something the same. I'm still going to run out of room despite trying to plan well, but I think that'll be okay. And the last color was yellow, something like this with a plus, and then something like that. Awesome. So derivative of x is 1. This is where it stays the same. Keep y the same, and then the derivative of y, remember your implicit. It becomes 2y to the first times the derivative of y, which in this case, because of the ddx, is dy dx. Minus, on the other side, 3x squared, technically times 1, but nobody's going to write the 1, and so I won't either. We keep y the same, but now we keep x the same. That's x cubed. And then we multiply by the derivative of y, and the derivative of y with respect to x is dy dx. Trying to clean this up a bit, I'm going to keep my 2 terms that have dy dx on this side, and I'm also going to factor out dy dx. Don't forget that when we distribute the negative, both of these last 2 terms are negative. So that's going to look something like this. We're going to have dy dx factored out of x, well, let's say 2xy, that came from up here, minus, and then over here it looks like just x cubed, equals, and then on the other side we need to subtract everything else off that didn't have that, so there's going to be a negative y squared from over here, and we're going to have to add this one over, so plus 3x squared y. And then finishing off, I think we need to divide by our 2xy minus x cubed, so that gives something like this, plus 3x squared y divided by 2xy minus x cubed. And how did I do? I did pretty well. I probably should have switched the order up here, put that positive 3x squared y first, and then minus y squared after, and then it does match. Go us. Double product rule, factoring, but nothing too weird. However, the second one is much more weird, because we have a dt down here, and you might notice that in the original equation there is no variable t. Well, what do? We need to introduce that dt. The reason that there is this dx down here is because we did d dx of each side. So it seems to me then that we should probably go through and do d dt of each side of this equation. And that seems very, very weird. You're like, why are we introducing a variable? We're going to talk a little bit more about this notation and what it means to be with respect to a variable today. So I'm just going to ask that you hold tight for a quick second, and then I think I'll be able to answer that question as time goes on. So we're going to take the derivative of x squared plus y squared on the left side and of 10 on the right side. The derivative of a constant is always 0. When we do this derivative over here, though, it's going to be 2x to the first. And then remember I said over here, nobody writes the times 1. Why would we do that? Well, this might be why. Because we did the derivative of the power, but we left x the same. So we do need to multiply by the derivative of x. And normally, if this was d dx, then you would have something like dx over dx. They'd cancel, and you'd say it's 1. In this case, though, it's going to be dx dt. And so things are a little bit different now. So we have 2y to the first times, and you guessed it, derivative of y dy dt. All right, let's clean this up a little bit. They asked us, I think, to solve for dy dt, didn't they? So that's this guy over here. So let's subtract the other fraction over. That leaves me with 2y dy dt equals negative 2x dx dt. And then I think we could probably divide off the 2y here. In fact, we could divide both sides by 2 just to get rid of that. And then we could divide both sides by y. So that gives me negative x times dx dt divided by y. A nice application of that implicit differentiation that we worked on earlier this unit, where we introduced a different differential, d dt this time, instead of something that we've done in the past. And by doing that, we were still able to take the derivative, even if we're not quite sure why we would want to do that. So let's pause for a quick second on what does this d dt thing mean. We're going to go to, strangely, a real-world problem and discuss that. And then we should be able to bring everything back together about what the heck this process, this related rates process is. So let's rock and roll. A 13-foot ladder leans against a wall. The base of the ladder is 5 feet from the bottom of the wall. The ladder begins sliding down the wall. Okay. A. Draw a picture of a situation assuming a vertical wall. I can do that. We have a ladder, something like this, right? And of course our ladder is going to have these nice little rungs that are going across it. And they're telling us that the ladder is 13 feet. So this guy right here is 13 feet. Nothing awful. But I don't think that's ever going to change. We're assuming it's not like an extension ladder. And then they're also telling us that the base of the ladder, so right here, is 5 feet from the wall. Okay, doing all right there. And then how far up the wall does the ladder reach? Well, to me, I think this is a right angle. This looks like a nice application of our Pythagorean theorem, where we're looking for, instead of h or b or abc in this case, I'm going to just keep this as x and y. Maybe we can picture this as like an xy axis. So I'm really interested in what is y here. So we, of course, have 5 squared plus y squared equals 13 squared. So 25 plus y squared equals 13 squared. I think that's 169. And then y squared, if we take off 25 from there, what are we going to get? That looks like 144. And so when we square root, it's not going to shock you when we get 12. Now, hopefully you would have recognized this as a 5, 12, 13 special Pythagorean triangle, or that's a Pythagorean triple is what we call it. But if you didn't, we of course have the Pythagorean theorem. We did include feet with our label whenever a problem gives you units. We need to continue those units all the way through, and although you don't have to put it on each individual term as we go through, you do want to include those units at the end. And that's a general rule for the AP exam, is if they give you units in the problem, they will expect you to give units in the answer. Of course, they usually will say, put units in your answer, but it's never a bad thing to do. All right, next up. After 1 second, the ladder is now 6 feet from the bottom of the wall. How much did its length from the wall change? Well, that's, not too hard, but I should probably draw one more picture, I think. So we have this wall over here. Okay, there's a nice solid wall, hopefully. And we have our ladder, which I'll do in black again. Okay, and they said, cool, now the length of the ladder from the wall is 6 feet. I'll zoom in on that. And they're like, well, how much did that change? Well, if originally it was 5 and now it's at 6, it seems to me that x got 1 larger. So we could either say it in words. A lot of times you'll see a change in x. The change in x was positive 1, right? We increased the distance by 1. If it had gotten smaller, it would be negative, and that's not too hard. However, they are also saying how much did the distance up the wall change? Well, if this base of the ladder is sliding out, then the top piece is sliding down, which means that no longer is the top of the ladder going to be 12 feet from the wall. Now it's got to be smaller. We've really closed the distance. How do we show that? Well, let's just use our Pythagorean theorem, because again, the length of the ladder isn't changing. That's always 13. And so I think we can use our Pythagorean theorem here. We have a new y value over here, which is fine. I'll just reuse the variable. Why not? And we know this is going to be 6 squared plus y squared equals 13 squared. So we know that y is going to be 169 minus 36, sorry, y squared, which is going to give us that y is equal to the square root of 169 minus 36. 9 minus 6 is 3. 6 minus 3 is 3. Looks like the square root of 133. Well, let's do that math really quickly. I probably want a decimal here, so I'm going to do the square root, which apparently I've lost, of 133. And I went outside, so that was obnoxious too. Second try, 133, and then we'll do control equals to get the approximation, 11.532 feet. Approximately 11.532 feet. So what was the change in y then? Well, my change in y, which is what we just found over here, how much y changed by, it was originally at 12, right? But now it actually got smaller. So to show a smaller change, that's got to be negative. And then how far apart are those two? We can just subtract them, whether top minus bottom, bottom minus top, doesn't really matter. I'll just do minus the answer, and that gives me 0.467. 0.467. Again, showing that the y's change was negative, meaning that the y value got smaller. Now, what does that tell you about the speed of the ladder? That's a really fascinating question here. Well, maybe we can think that this change in x, this changed by 1, but when we changed the base by 1, you might have expected the height to change by 1. Did it? Well, no, the height changed by negative 0.467. The height didn't change as quickly. When the x changed by 1, the height only changed by close to about 0.5. And to me, this was mind-blowing. Like, absolutely, I didn't really understand this until I started teaching it, that when you have an object that's moving, especially at an angle like this, not all parts of the object move at the same speed, which is pretty darn fascinating, right? What we can tell right here is that when the base moved out by 1 foot, right, the height only dropped by half a foot. And so however fast this guy's moving, this is the same amount of time, right? This is over 1 second. Over 1 second, this moved 1 foot per that second. However, the height decreased by 0.467 feet per that second. And so that means that if someone's standing up here versus someone standing down here, they're actually moving at 2 different speeds. Again, this is a little bit wild to me. Another comparison maybe to think about is, let's say that you go to a carnival and there's that merry-go-round, right? We've probably all seen or been on one at some point. And usually the way the merry-go-round works is they have like a whole bunch of like horses or whatever things that you can ride in a middle circle, and then this concentric circle around the outside has another set of animals to ride, and then we have another one out here. Well, think about I should have drawn this better, that was silly. 1, 2, 3. There we go. Think about if 3 of these are lined up, and you've got person A sitting here, person B sitting here, and person C sitting here. Well, person A is going to make a trip all the way around here, and clearly that's a small circle. But because on a merry-go-round, these are fixed, they don't move at different, like they're not moving rings on the inside. While person in red is moving around, person in purple is moving around, and they're parallel to each other all the way around until they get back here. But in the time it took person red to complete one circle, person purple also completed the circle, but they completed a bigger one. And in fact, yellow did the same thing, but it completed an even larger circle. So if they all finish at the same time, but they had to go different distances, what does that tell you about their speed? Well, it tells you that even though you're fixed on these inanimate objects, you're actually moving at a different speed, which is still very hard for me to comprehend. And I find that this related rates topic really falls on 3 types of brains, where you have brain number 1, which is not my brain, where people go, of course you move at different speeds. That makes so much sense. Obviously, someone's on a ladder up here and someone's down here. Of course they're moving at different speeds. And then you have a brain like mine who says, well, mathematically that makes sense, and I guess I will accept it. And then you have brain number 3 who says, I don't really know what's going on yet, I need more. And that's fine. You will have more context. We're spending 3 days on this topic, so don't stress. Let's go ahead and define a few more variables here, though. Y is, as mentioned before, ignoring the merry-go-round idea, Y is going to be the distance from the top of the ladder to the ground. And so then we're going to introduce a new variable, and this variable is going to be dy dt. And we're going to be a little bit more in depth about what each of these mean then. We are going to take dy, where d is essentially going to be like that triangle, that change in. And there's a little bit more when we make it this d something, but we'll expand on that as we go through. Dy is going to mean the change in the y values, versus dx is going to be the change in t values. Now, these values are a little bit vague. So y values is just going to be the vertical distance, right? Nothing too bad. Okay. However, what do we think t means in this case? We're talking about dy dt. Well, for pretty much every related rate problem, we are always going to be curious about how things are changing as time changes. So in this case, and pretty much every case for the next few days, t is going to be a variable that represents a change in time. So in this case, it's going to be the time in seconds. And what calculus allows us to do is it allows us to introduce a variable that might not have been in the original equation. Our original equation was the Pythagorean theorem up here. And it allows us to introduce a third extra, or not third, there could be more than that, an extra variable that wasn't in the problem, and let us measure how all the other variables change based on how this extra variable is changing that we're inserting in. So maybe we have my dog is coming in to play with his squeaky toys right now, of course, because, you know, why not? So maybe we have this problem where we know that the height and the base are changing, but we're curious as to how each of them is changing as time goes on. Well, this allows us to look at them separately. It says, how does y change as time changes? And how does, down here, x change as time changes? And that's a really nice way to compare 2 different speeds. In fact, we see this slope as a speed very often, and we'll go more into that as well. So the question says, what does dy dt represent? It's the change in y values over the change in t values. So really it's the change in the vertical distance as time changes. In this case, is it positive or negative? Well, dy dt will always, and I'm going to put just less than 0, but you can of course say negative as well. Dy dt will always be negative because we are decreasing the distance between the top of the ladder and the base. And whenever you decrease distance, think decreasing slope, that is a negative slope. Now, I have a feeling that you'll be pretty comfortable with the next part then when we discuss dx dt. Of course, this is going to be the change in the x values, which in this case is the horizontal distance, over the change in t values, which is, again, the time in seconds. Because we are pulling the base of the ladder away, that is increasing the x value, and anytime you have an increasing slope, an increasing derivative, that derivative will be positive. So dx dt is greater than 0 in this case, or positive. Now, trying to relate this all to something we know in the past, let's think about the equation d equals r times t. This is an equation you're supposed to have seen before, especially if you've done any word problems in past math classes. We have d equals r times t, and I'm going to define them going straight down. Usually you are told that this stands for distance equals a rate times a time. However, I don't like that formula. It will work for today. Really, I prefer the formula A equals R times T, where it's an amount equals a rate times time. I mean, this formula still works for like how much money you make. If you work for a few hours at a rate of $20 an hour, you multiply those together to find the amount that you make, versus distance is a very specific type of an amount. It's the amount of distance. But why not do the amount of money, the amount of distance, the amount of anything? So you can think of either of these, and if you want, we can stick with d equals rt. But what does that mean about the speeds of the top of the ladder versus the bottom? Well, let's just look at one of them. Let's look at, I don't know, this x value 1 right here, right? So we had a distance traveled. Well, how far did that ladder at the bottom travel? It traveled 1 foot. We don't know the rate yet, but we do know that the time, well, how long did it take over 1 second? And I should honestly probably keep my units in here too, something like that. So if I wanted to solve for the rate here, my rate is going to be 1 foot per 1 second. And that, of course, is going to be the rate of the horizontal distance. 1 foot per every 1 second. However, what if I wanted to look at a second rate, where the second rate I'll do in a different color. This is where instead of changing 1 foot, we changed by, and this is our number up here, right? We changed by negative 0.467, let's make sure I got that right, feet. And that tells us it's some rate, but it was times 1 second. And if I solve for that rate, I get that my ladder moves at negative 4.467 feet per every 1 second. And here is my rate of the vertical distance. And so by comparing these two, we can see that these two rates are certainly different. Of course, when I say rate, we should really be thinking, oh wait, this is how the vertical distance changes as time changes. So dx dt is just a rate of change, right? Same thing over here. This is dy dt, the vertical distance. It's how the vertical distance changed over time. And that's all a derivative is. It's a comparison of two changes to each other. And we can really compare anything. We could compare how the vertical distance changed as the horizontal distance changed. And if we did the vertical distance over the horizontal distance, it's dy dx. Right? We could compare as time changed, how did the vertical distance change, and we could do dt dy if we wanted. But we're used to seeing distance per time, right? So distance per time, feet per second sounds better to us than seconds per feet. And whenever we see that, a lot of times we'll think of this as a speed. A rate is a speed. Now, there's going to be a lot more into this as we go throughout the semester, but this is a really nice introduction into the fact that we had two rates in a situation. We wanted to study how those rates changed over time. But related rates, which is our topic on the second page, really the whole topic here, revolves around the idea that if you know a rate of change, like a speed on the previous page, about a certain part of a problem, let's say the bottom of the ladder, then you should be able to find another rate of change in that scenario by examining the relationship between the variables in the situation. Essentially what that's telling us is if we know this rate, we should be able to find this rate with one simple equation. There is an equation that relates these two rates together. So related rates is all about comparing multiple derivatives together with a single equation. Now, let's go ahead and put a couple things down in here. Of course, as derivatives, calculate the rate of change of a variable, right? That derivative, this instantaneous rate of change. We can use calculus to accomplish the goal of identifying an equation to relate rates together. Generally, rates are given as distance over time. And so if you look at that as a fraction, we can measure the rate as the change in distance over the change in time. Sometimes you'll see it as d distance over d time, or earlier you might have seen it as delta distance over delta time. And for all intents and purposes, it's pretty much the same for what we're doing here. Again, we haven't really discussed the difference between this d differential thing and this delta thing over here. And there is a difference, but so we're going to say for today that d really means delta, even though that's not quite right. So we want to see the change in time. That's almost always what happens with a related rate. What happens is one thing changes over time as another thing does. So for today and for the next 3 days, we're actually going to be taking all of our derivatives with respect to time. So we're going to be doing d dt to both of our equations, or to both sides of an equation. And it's weird because the equations aren't actually going to have t in it. Now, I have found that students really struggle with related rates, and they don't actually struggle with the calculus. The calculus piece is very small. Instead, what they struggle with is how to set up the problem, because there's a whole bunch of steps, a lot of different components, and they've asked in the past for just some sort of steps or like a guideline of what we should do. So this is what I've come up with over the last couple of years, and students have said that it's super helpful, so hopefully it is for you. Of course, if you have any suggestions, I'm always open to it. All right, so what we're going to do, and this is going to be a lot easier with an example problem, but I'm going to quickly go through this, and then we're going to go back and see this more in depth on our first problem down below. The first step is always the know, meaning we're going to list what's given and what's constant. Almost always you are given a rate. This is what's most important. We need to know a rate at the beginning. And we're going to write that rate in calculus notation. Is it as y is changing as time, as x is changing, as a radius changes, as a side changes over time, so on and so forth. After you have what you know written out, then you're going to need to list out what you want to know. And I just call it the want. And what that want is will also be a rate. We want the rate of something. Now, almost every problem we see is going to give us extra information at this point. And it doesn't matter where you put the extra information. I usually put it in the want section. Some people will put this extra information in the know section. It's up to you. But usually what happens is this extra piece of information isn't always constant. Meaning they're saying, well, at this exact time that we're talking about, we want the rate when this is happening. Versus the know is something that's always constant. We know the rate is this always. The third step is drawing a picture, which I try to do unless the pictures are beyond my pictorial production, which does sometimes happen. And then we get to the equation part. The equation part is, okay, cool. We know a rate. We know we want another rate. We need an equation that connects the two of them. But we don't actually use any derivatives to start. All we do is we just take a look at the variable up here that is not the calculus part of it. We just look at y. And then over here, we look at the other variable we might be interested in, and we just try to write a non-calculus equation that relates those two variables. Once we get an equation that has both those variables in it, then and only then do we take the derivative. We take the derivative of both sides using d dt. It is okay to use y prime and x prime. I much prefer, though, dy dt and dx dt, because as soon as you get three variables going on and you see y prime, you might say, well, wait, is y prime dy dx? Or is it dy dt? Which one of those? And so that y prime, that Newtonian notation, really doesn't give us a clear enough picture, so I really suggest that Leibniz form that's written there. And then last but not least, once you've taken your derivative, you take the knows and wants, you plug everything into your derivative, and solve. Now that was a ton of information, so let's try to make this make a little more sense here. We drop a pebble into a pond. It creates a ripple effect in the form of a perfect circle that's expanding outwards. We've, I think, all done this at some point, right? You drop in this pebble, and then on the outside you get kind of this little ripple, and then out there there's like another ripple, and then there's another ripple after that, and it's rippling outwards, generally pretty evenly too, as long as you drop your pebble straight down. If you throw it at an angle, even still, then it's, pretty decent. We're going to assume that this is a perfect world. Pretty much all math assumes a perfect world, and you can add extra variables in if you get to the physics or real world side of things. So, creates a ripple effect in the form of a perfect circle that is expanding outward. The radius of the circle is increasing at a constant rate of 2 inches per second. Part A. At what rate is the circumference increasing? The circumference, of course, of the circle of your ripple. Now, I'm really just assuming here that there's just one ripple, and this ripple, of course, as time goes on, is going to get bigger. So the next time we measure this friendly old ripple, it's going to have a larger circumference, and so on and so forth. Okay, so at what rate is the circumference increasing? Let's go to our chart. First thing, know. What rate do we know? Well, rate. The radius is a circle. It's a constant. Found it. Rate. A rate is always going to give you some amount, usually a distance, per some time. Right? We talked about that earlier. The rate is distance over time. So we need to write this rate, and I always like to write it like this. It's 2 inches per seconds. S is a pretty common abbreviation for seconds. A lot of times I write SEC just to give more information. You don't have to, though. So it's 2 inches per second. And I know you can write this as 2 inches per second, but I think people forget that there's a little bit that this is still a fraction, and technically this unit goes with here and the seconds goes with the denominator. So really this means 2 inches per every 1 second. Of course, you can just say 2 inches per second. Now, the problem, though, is what is this in calculus notation? They asked us to write it in calculus notation. Well, what is this measuring the change of? It's measuring the change of the radius of the circle. So we probably need to define a variable. I'm probably going to say that r equals the radius. That makes a lot of sense. And so this is showing us the change in the radius, 2 inches. Inches is the radius. That's what we can measure it in. As what changes? Well, it's the change in the radius as time changes. So dr dt, the change in the radius over time, is 2 inches per every 1 second. Great. Now we move on to the want. What rate do we want to find? We know a rate. What rate do we want? Well, I think they tell us that pretty clearly out here. They say at what rate is the circumference increasing? So circumference of a circle, we have a new variable here. I'll probably define that over here where C is the circumference, spelling test, where C is the circumference. We don't even need to know anything about circumference right now. We just need to know that we want to find how the circumference is changing as time progresses. And these are always going to match. They're going to be dt for related rates. So we are basically saying, can we find an equation that tells us as the radius changes, how does the circumference change? All right, well, let's go further then. The third step is a picture. We already did that. So I think after this, we are probably going to need an equation. Now, when we do the equation, there's no calculus involved. My equation is just going to relate these two variables together, circumference and radius. So we need an equation, has to be an equal sign, and it has to relate radius and circumference together. So maybe you might think of a circle here that has a radius, and we also might remember that the circumference runs around the circle. I'll get rid of that confusing other piece here. Runs around the circle. It's the total distance around, and hopefully you remember the equation for circumference of a circle. You could either write it as 2r pi. A lot of people say 2 pi r. I've never been a fan of that. I like 2r pi, or you could remember if you double the radius, that's also the diameter times pi. Well, which one of these do we want? We don't want the one with diameter and circumference. We're trying to write an equation that only has radius and circumference in it. So I think that's going to be this guy over here. Okay, so my related equation is going to be the circumference equals, and I know I said I don't like 2 pi r, I'm just going to completely go back on it right now, and I'm going to write it as 2 pi r. The reason I'm doing that is because I wanted to leave the variable at the end. This is a coefficient, 2 times pi, 2 times 3.14, 6.28 approximately. This is a coefficient. I know I'm going to have to take the derivative, and we know when we take derivatives, this coefficient just hangs out front, and that's a little bit easier than writing it 2 times r times pi, because then you're like, wait, there's 2 coefficients, what do we do? Things get wild. So I think that equation's probably fine. Then we have the equation, but our whole goal is to write an equation that relates the two derivatives together. So this is where we actually get some calculus. This is where the derivative comes in. We need to somehow create the term dc dt and dr dt, which I think means to me that we need to take d dt of each side. Okay, so d dt of c and d dt of 2 times pi times r. Well, there's nothing too crazy here. d dt of c, we should be pretty comfortable with this from our implicit, becomes dc dt equals 2 pi as a constant, so it stays, and the derivative of r is dr dt. And look at that. We now have a derivative equation that relates two rates together. It tells us if we wanted to convert from the rate of change of the radius to the rate of change of circumference, we just plug in something for the rate of the radius, multiply it by 2 pi, and now we know how fast the circumference is changing. And so, and I'm going to need this extra space down here, so we get to our last step, which is the evaluate part. Evaluate or substitute. Substitute's probably a better word, but I already wrote evaluate, so I'm rolling with it. We are looking for dc dt, and we know, back up here, that that dr dt is 2 inches per second. I really suggest you keep your units in here. You don't have to. It won't change too much, but it's not a bad idea. And the reason I suggest that, and I also suggest you work down instead of side to side. I think you lose units if you work side to side, is because we'll see this 2 pi, this is unitless, it didn't have units on it, times 2, which gives us 4 pi inches per 1 second. Of course, that's probably not how you'd see the answer. Most people would probably write this as 4 pi inches per second. Nothing too terrible. We found that as the radius is changing, right, or when the radius, as the radius is changing at 2 inches per second, the circumference is also changing, but it's changing way faster. It's changing at 4 pi inches per second. 4 times pi, it's about 12-ish. So for every essentially 2 inches the radius changes, the circumference changes by 12, and that's a pretty huge increase, right? And that's a related rates problem. We're going to do one more and then call it good for today. You only have a couple practice problems too, and I like to keep it easy the first day in just so we get used to the setup more than anything else. So the last one. At what rate is the area increasing when the radius is 6 inches? Okay, here we go. No. Did they give us any rates in here? They didn't, so I think the only rate that I'm going to use is the one that we were given before. So we know that dr dt is again 2 inches per second. Nice. Let's do the want, and I'm going to try to work sideways to save a little space here. What rate do we want? We want the rate the area is increasing. The rate of the area, that's got to be dA dt. And I'm going to switch colors again. We'll go in purple. We want dA dt. Okay. And when do we want the change of the area? Oh, they gave us something else. They said when the radius is 6 inches. Now, this is going to be different than part A. On part A, the circumference and the radius are both changing constantly, but at an even relationship. There's no other variables down here, so they don't really depend on anything else. They're perfectly related to each other. However, what's going to happen is when we talk about area, the change in the area isn't just going to depend on the change in the radius. It's also going to depend on how large the radius is at a specific time. And this is really tough for people to grasp. It's basically saying that when you have a circle, and I'm going to erase this so don't stress. If you have a circle when the radius is 2, the area itself is changing at 1 speed. But then if you had a circle with a radius of 5, the area is changing at a different speed. It's probably going to be picking up, but that would be my guess. So the area changes at different speeds, and so you're not going to get a constant like this. You're not going to get a constant answer. So what we have to do is we have to say, well, when are we most interested in when this radius or when the area is changing? And someone said, well, I basically want you to take a remote. Think of it's an old movie now, but think of the movie Click with Adam Sandler, where he has a remote where he can pause time. They're basically saying the area is getting bigger and bigger and bigger and pause. And so time absolutely freezes. They're saying, okay, right now the radius is 6 inches. At this exact time, how big is the area getting? Okay, and so that's what we're doing at this point. So when they say when the radius is 6 inches, we're actually going to add this on to the want part. So I'm going to say we want dA dt when r equals 6 inches. And I always put it in the want so that we don't confuse it. We don't think that's something constant. The radius isn't always 6. If the radius is always 6 for a circle, is the area increasing at all? Well, no. If the radius is always 6, the circle's not moving. It's constant. And so dA dt will be 0. It won't be changing. But this is just saying it's changing. We're pausing. All right, enough of that. On to our equation. Well, somehow we need to relate then the area of a circle. I should be doing this down here. The radius of a circle to the area of a circle. And I bet you guys know this one. Pretty much everyone remembers that area equals pi times the radius squared, pi r squared. Good so far? Let's move on to the derivative. The derivative is, of course, taking the derivative d dt, get used to it, you're going to be using it a bunch the next couple of days, of each side, d dt of a and d dt of pi times r squared. Well, d dt of a is going to be dA dt, the change in the area as time changes. d dt of pi times r squared, pi is a constant. The derivative of r squared, 2 comes down, r stays the same to the first power. But I said the magic word, r stayed the same, so we need to multiply by the derivative of r with respect to t, which will be dr dt. And so now picture or take a look at this relationship. It says that not only does dA dt depend on how fast the radius is changing, it also depends on what the radius is at that time. So dA dt is a function with 2 inputs. We need to input r and dr dt. So it shouldn't shock you too much then when I get to the substitute part, when I substitute or evaluate this equation, that something like this happens. So we get dA dt equals pi times 2r to the first, which I'm not going to write, times dr dt. Well, dr dt we know is 2 inches per second. And what about r? Well, we want to know when r is 6 inches, what the rate of change of the area is, so I'm going to put in 6 inches. And notice I am careful about my units here, and you don't have to put in units until the very final answer, but I find as long as the problem's not too complicated, like if there are 30 terms, I wouldn't want to write units every time. But there's 2 terms here. I mean, why not, or 2 factors, why not put them all in? Because what I find happens is if you put in the units, it's much easier to keep track of our dimensional analysis. And I'll explain that right now. So we can treat all of these as being over 1. When you multiply the entire bottom, including the units, I end up with just 1 second. When you multiply the entire top, 2 times 2 is 4, 4 times 6 is 24. The pi tags along, but then don't forget to multiply your units. Oops, sorry, and I've highlighted more than the units. Your units as well. We have inches times another set of inches, which means in this problem we have square inches. And so if we wanted to simplify this down a little bit, we could say the area is changing over time when the radius is 6 inches at a rate of 24 pi square inches per second. Now, why does square inches make sense here? Well, I think it makes sense because area is a 2-dimensional thing. 2-dimensional being, probably not a 2-dimensional thing. Sometimes people struggle. They're like, wait, how do I know if something's 1-dimensional or 2-dimensional or 3-dimensional or multi-dimensional? I think it's easiest to picture an axis. You start with a number line, or an axis if you want. This number line is one-dimensional because it extends in one direction. I mean, technically two, but this is the same direction. This is the side-to-side direction, the horizontal direction, the dimension of width, if you want. If we want to extend in a second direction, we can do that. We can add on a dimension of height. And so this is something that's two-dimensional. If you wanted to extend in a third dimension, this one's going to be much harder for me to draw, we would have to extend straight up, right? And so this would give us width, height, length. Maybe I should have called the other one length, but either way, this is going to be our third dimension. And so if you wanted to take a look at a few common shapes here, right, you have a line, which is, of course, one-dimensional. Okay. You have a rectangle. Think about that. One dimension, two dimension. This is, of course, going to be 2D. And then you could also, of course, get yourself a nice prism over here. That was not the world's best drawing. That's okay. Don't judge me too much. Sure, whatever. And this is, of course, going to be three-dimensional because it has length, width, and height. And people are like, well, that makes sense here, but what about a circle? Circles are so strange. Well, two ways to think about it. This circle has both, if we start here, height and width. But the second giveaway actually has to do with the units. If you see square inches, it is two-dimensional. You have inches one way times inches another way. You have inches times inches, and whenever you multiply two different, or two even the same, two-dimensional quantities, it increases the dimensionality. So we went from one-dimensional times one-dimensional gave us two dimensions. Okay, and so we get a two-dimensional rate of change. It's as the area changes over time. Again, pretty straightforward short lesson today, though straightforward might be the wrong word. The next 2 days we are going to step it up a little bit, but I really want you to try to hit into your mind that know, want, equation derivative, and then evaluate. And they really come in pairs, right? The know and want is the setup, the equation and the derivative is the math part, and then the calculus part, and then the evaluate is just plugging in numbers. So thank you for your hard work. Good luck with your independent practice tonight. It's not meant to be super long, and I'm excited to see you next class for more related rates.